Okay, so this lecture is about Green's theorem, and it's going to be the first of two lectures about Green's theorem, which I've written up here. But let me just first give you a little bit of context here. So the Green's theorem is one of the three fundamental theorems of multivariable calculus that we will cover. I will say that I will, in my opinion, there are three which are really, really important, and those three are the ones that we're going to be covering over here. The three that we're going to cover are the Green's theorem, then Stokes' theorem, and also the divergence theorem, which is also sometimes called Gauss's theorem, but we'll get to those later. So this is about Green's theorem. Okay, but all of these fundamental theorems, they essentially generalize the single variable fundamental theorem of calculus. So you might remember this is one way of writing the single variable single variable fundamental theorem. And what's really interesting about it is that you've got a derivative and then you've got an integral. You take a derivative and an integral, and it's saying that you recover the function. So it's connecting together the two quite different concepts of differentiation and integration. But I want to point out something rather important over here. If I look at the left-hand side, you're doing an integral over this entire green region, right? So you need the value of the function, or in this case, the derivative of the function at every single point in this interval. But if you look at the right-hand side, all you really need are values at the boundary of the integral of this interval, which means that the fundamental theorem, as expressed over here, is doing something rather interesting. It's connecting something which is in the interior of the interval to something on the boundary of the interval. And the three fundamental theorems that we're going to cover here, including Green's theorem, also maintain that spirit. So they do establish connections between derivatives and integrals, just like you have over here, but they also have the spirit of converting integrals in the interior of a region to something on the boundary. Right. So let's get to that as we proceed. Yeah. So here's the other important thing about this, right? It's a connection between derivatives and integrals. Okay, so let's get to Green's theorem, right? So this is sort of a simple version of Green's theorem, and we'll sort of push this a little further as we proceed. So now Green's theorem is restricted to R2, so we have to be in R2, and so let R be a region in R2 with boundary given by this thing over here. So here's a sort of notation that I'm going to follow. And actually, I made a mistake over here because I've got this the wrong way. That should be in this direction, right? So we'll talk about that a little bit more later. Okay, so you got a region, and the boundary is given by this. So this is just notation, right? So that's a partial derivative symbol and R. So this we use as a notation for the boundary of R. Now, R is this entire region over here. So the boundary is where, well, imagine that you're an ant in this region and you want to leave the region. It's where you need to cross. So the boundary is actually this bounding curve. So the boundary of a two-dimensional region in R2 is going to be a curve in general, right? So this is a curve. So this let me call it dr, if you will. This dr is actually going to be a curve. So we have a situation where you got a region like this, and its boundary is a simple piecewise smooth curve. So what does this mean? Simple means that it doesn't intersect itself. So you can't have figure 8 curves. Those are prohibited. And piecewise smooth, right? So you can have a curve which is smooth like that, and then it has a wedge like that. That's okay, because it's smooth up to the wedge, right? So it's smooth up to the wedge. So you can have a few places where it's got these little cusps, if you will, but you can't have these sort of infinitely sort of crazy curves. That's prohibited. Okay, simple piecewise smooth curve. Then what's the conclusion? Well, it's related to two functions. So right, you need two functions, u and v. And they are scalar fields, right? So u is a function of x and y because we are in R2, and this R here corresponds to that, right? So it's you're in R2 here. So they are C1 scalar fields. So at least the first derivative is continuous scalar fields in this region, right? So throughout this region, these functions are differentiable, is what it's saying. And then here's the conclusion. So the main conclusion is this thing over here, which seems like a complicated thing, but what we're going to do is we're going to dissect this as we proceed. But what I really want to point out here is that this, what you see on the right hand side, is a double integral over R. So you have a region over here. So you're doing a double integral, so it's dx dy. So I can think of that as dA, of course, right? So it doesn't matter in this notation. I can write this as dy dx as well. It doesn't really matter. So that's my d capital A. So differential area element, and I've got a function over here which I construct from these two functions that I've given. So what I have on the left-hand side is an integral, a double integral over the interior here. On the other hand, what I have on the right-hand side is something quite different. It's an integral over over dr. And what is dr? Well, dr is the boundary. It's this curve. So what this is a integral all along the curve. It's a line integral. Yeah, I put this this closed symbol over here because it must be closed because of the nature in which we've defined it. Right, it must be a closed curve, because if not, it's not going to separate out the region R from the outside. Right, so it has to be a closed curve for Green's theorem to apply, for it to be a boundary of a region. And what is it? Well, you have to do u dx plus v dy. That's your line integral, right? So remember that u is a function of x and y, and v is a function of x and y. And as we're traversing the curve, both x and y are changing. So you can't just do this in a very simple-minded fashion. You have to follow the procedures that we have for line integrals. So it's a connection between these two. So one is an integral over the interior, one is an integral on the boundary, right? And then there's some issues related to derivatives as well. Okay, so in this sense, it's in the same spirit of the fundamental theorem of calculus for single variable things. It's connecting integrals over a region to integrals to something on the boundary, right? In this case, on the boundary, it's going to be an integral because the boundary is itself a one-dimensional object in this case, right? So it's got that spirit, and it also has this connection between derivatives and integrals. Okay, okay. Now, some points that I want to make before I actually prove this. So counterclockwise or anticlockwise is positive for the closed curve, right? So we have to, so in this convention, we have to go anticlockwise because that's the positive, in mathematics, that's the positive way. You might think of polar coordinates, for example. So from the positive x-axis, you go anticlockwise, right? Anticlockwise is always the positive for the closed curve. So the reason why that's important is that when you're doing a line integral, the direction you go matters. If you go in the opposite direction, you get negative what you had before. Okay, so that's one of the things that you can see. So the right-hand side here, is given by this, and I just want to highlight the fact that this actually is an integral of the form f dot dr. And why is that? Well, if I think of my dr, my general line element is going to be dxi plus dyj. Yeah, that's going to be my line element. So if I define this vector valued function f, whose components are u and v, then what I have inside here is just f dot dr. Yeah, so what this is just f dot dr around a closed loop. And integrals of this sort are sometimes called a circulation integral, because what you're doing here is you're projecting f all the way onto the curve, and you're integrating all the way around the curve, right? It measures some sort of rotation effect. Okay, so this thing is a line integral. Okay, finally. This is the point that I made before. What Green's theorem does, it connects a double integral, in this case an area integral, with a line integral, and a line integral around the boundary. Okay. Let's get to this proof, right? So to do the proof, what I want to do is I first want to consider what I'm going to call an elementary region. I'm not going to get hung up into defining exactly what this is, but just my requirement is I need to be able to express the area integral as an iterated integral. I'll tell you what that means in a moment, if you can't remember what it is. It has to be expressed as an iterated integral. So here is an example of such a region. So R is the interior here, and dr is going to be this closed loop. Right? So in this case, I can see that this curve goes from x equals a to x equals b, and then what I can see here is that I have these. I can split this into two, right? So the lower boundary, I can call that a curve y equals phi 1 of x, and the upper boundary, I can call it a curve y equals phi 3 of x. Yeah, so this lower curve I'm going to call C1. Yeah, so lower curve I'm going to call C1, and upper curve I'm going to call C3. So this is exactly the condition to be able to write this as an iterated integral. So an iterated integral is when you write it in the form dy dx or dx dy, and you're able to put down very well-defined limits over here, right? So forget what's inside the integral for the moment. I just concentrate on these limits here. So I'm doing an iterated integral here. So dx, x goes from a to b, and then if I pick a particular value of x which is between a and b, y goes from, well, this value to that value. So it goes from phi1 of x to phi3 of x. So I'm able to write this as an iterated integral, and that's my condition for this to be an elementary region, right? So if I have something like this, then I'm not quite able to do that. Okay. So what am I saying here? So I'm saying something a little bit more here. I'm taking a particular function, and the function I'm taking is negative du by dy. Why am I taking that? Well, it'll all come out in the wash as we proceed. I'm taking this function and I'm doing the double integral of that function over the region R, and under this condition I can write this as an iterated integral. So here it's a function negative du by dy, and I'm writing it in this case in the form dy dx, right? And I've already explained why these limits work in this case. Now, once I've written this as an iterated integral, I notice something nice. So when I'm doing an iterated integral, what you normally do is you work your way outwards. You think of these as sort of nested brackets, right? So you do your y integral first, and then you get some stuff over here which can depend on x, and as it will, as you can see over here, and then finally you do your x integral. Now this y integral is actually quite trivial because it's telling you to differentiate u with respect to y, and then take dy and then to do the integral. So by the standard fundamental theorem of calculus, because when you're doing this y integral, you're essentially just integrating, you've picked an x value and you're just integrating along this straight line, and y is varying as you're going along, that x is not when you're doing this iterated integral. So this I can consider this very much in the spirit of single variable calculus, keeping x fixed. And if I do that, this is just telling me I take the y derivative of a function and integrate it with respect to y. Well, that's a standard fundamental theorem of calculus. So that standard fundamental theorem of calculus tells me that this gives me this. I recover u because I've differentiated and then integrated it. I just get u, and then I need to evaluate it at the upper point and evaluate it at the lower point, right? But there's a negative sign over here. So what I'm going to do is I'm going to sort of flip those two. So here is u evaluated at phi1, and here's u evaluated at phi3. But remember, u is a function of x and y. Right. So and these are y limits because that's associated with that. So when I evaluate at this point, so what I have is u at x and phi1 of x. Yeah. So that's what I have there. And the negative sign has been dealt with in this case by flipping the two limits. So I got this. Okay, so now this is of course a single variable integral, which I can think of trying to do, but of course, you know, I've got the x's here and so on. I'm not really going to do the integral, but I'm going to just notice something that I can do with the integral. So what I can do is I can split this into two. Right? So one of the integrals is going to be that, the other integral is going to be that, but notice there's a negative sign. Yeah? Okay, I'm integrating with respect of going from a to b. So when I'm going from a to b, and I'm just thinking of the first part of the integral, I'm going along this curve over here, right? Because this is phi1. I'm going along this curve. So I'm going along the curve C1. So C1 is my curve. This curve is C1. So this first part gives me that. I'm just writing it in that way. What about the second part? Well, the second part gives me this. So it's that dx, and what I need to do is I need to integrate this with respect to, well, what x goes from a to b. So x goes from a to b, but what I have here is phi3. So I'm going that way along this curve, yeah, because x goes from a to b. I'm going in that direction along this curve. Okay, so if I think of my C3 as going that way, and the reason I'm thinking of it like that is because my full curve C is this whole curve here. So I want to think of that as comprising C1 plus C3. Yeah. So if my full curve is going that way, and I think of C3 as going that way, what I'm being asked to do here is I'm going to go from A to B. So I'm being asked to go in the opposite direction. So I can compensate for that by putting a negative sign in front and writing down the integral over C3. There's a negative sign here. Along with this negative sign that I've argued, what I get is this. Okay. So this quantity, right, which I started with, I'm now said is equal to this here. But what's going on over here? So what's happening over here is that you're taking the function u and you're integrating along this. Yeah, that's what this is saying. And then here you're just integrating along that. So clearly what you're doing here is you're taking u and you're integrating into all the way around C. So this, I can just replace this with the integral of u over just C, which is the whole curve, right? C is dr. So here's that statement here, right? So here's the thing that I started with. I did all those manipulations, and what I figured out is that it's this thing over here. It's u. Oops, I got that wrong again. It's u dx. That should be an x. So it's u dx, and it's integrated all the way along that plus that, and when I do that together, that gives me dr. Okay. Well, that's pretty good. And then what I can do is I can now do something similar with by splitting it in the opposite direction. Right? So in the earlier case, I had x as my outer integral, but now I'm going to have y as my outer integral because I'm expecting to be able to do this as an iterated integral. So then I'm going to consider the function I'm going to consider is dv by dx. In this case, I consider negative du by dx, but here I'm by dy. Here I'm considering dv by dx. And if I follow exactly the same procedure and think about this, about splitting this as an iterated integral, that's one curve and that's another curve. So now you can see mysteriously why I went from C1 down here, why I went from C1 down here to C2 to C3, right? That was C1. This is C3. Well, the reason is because I want to call that part C2 and that part C4. So if I do that and I go through exactly the same calculation, what you will find is that when you do this, you're going to get this, right? So it's going to be the integral of v dy. Okay, so now we got these two expressions over here, and I'm going to just simply combine these two expressions. I have these two expressions. Let's simply add them. So if I look at what's going on here, so lots of little errors in this. So this is integral over r, not dr. So if I add these two things together, I realize that the left-hand side are both integrals over exactly the same quantity. It's over the region R. They're both dx dy and dy dx. They're identical to each other. That's just dA. So if I add this together, I get this. Yeah. So it's just that dv by dx minus du by dy, dx dy. Okay. What happens on the right-hand side if I add these together? They're again integrals over exactly the same curve, the boundary of this. So it's going to be u dx plus v dy. And this is Green's theorem. And that's exactly what we wanted to establish. However, in establishing this, we assume that we could do this iterative integral procedure. And of course, in general, we can't do that. So what if R is not one of these sort of elementary regions, right? What if it's a sort of complicated region, which is indicated by this thing over here? Well, then what you do is you split it up into lots and lots of elementary regions. You choose some small curves, as small as you want, right, to ensure that each of those curves comprises an elementary region. You split it up like this. Now, if I pick one of these, right, I'm going to call it Ri. I picked this one over here. If I pick this, then it's an elementary region. So I know that I can apply Green's theorem as we've just derived it. So I have this property over here. So the integral over Ri and this line integral over the boundary of Ri, which is going to be this curve. Okay, so I have this. Now, this is true for every single Ri. All I do now is I just add all of these equations together, right? So if I've got 100 different regions over here, I'll have 100 equations like this, just add them all together. When I add the right-hand side, well, I've got exactly the same function that I'm integrating with respect to dA, but I'm integrating it with respect to R1, R2, R3, R3, R4, and so on. So I just need to add everything together. When I add everything together, this just becomes the integral with respect to R, which is the entire region. Yeah, so there's no problem. This becomes the integral with respect to R. What about this? So for this, the one that I pictured here, what I have is I have an integral over that curve there. So for another curve here, I have an integral over that curve. So here I have an integral over that curve. So things are a little bit more complicated when I'm adding these things together. I'm doing these different types of line integrals. However, at every interior point, so let me sort of blow up a region over here. I might have two curves which look like this, the blue curve and the orange curve. And each of these is going in the anticlockwise direction. So there's my blue curve going in the anticlockwise direction. There's my orange curve going in the anticlockwise direction. So what this is telling me is I'm doing this integral over that, and I'm adding everything together. So I'm also doing the integral over that. Now notice what's happening at the region where these two curves touch. The blue curve is going that way, but the orange curve is going in the opposite direction. So if I do an integral, a line integral in that direction, it's going to be negative the value that I get if I do the line integral in the opposite direction. So what's going to happen is whenever there is a mutual connection, you're going to cancel. These line integrals are going to cancel. So everywhere where a curve touches another curve, I can just sort of get rid of it. All those things cancel. So this curve touches that curve at that point. So I'm getting nothing over there. And if you think about what's going to happen, then all the interior curves have to be touching another curve. So all the interior connections cancel. What are you left with? Well, curves like this, I have this exterior connection along the yellow part of dr. That's not going to cancel this. So nothing left to cancel with. So all of that is going to remain. And all of those are in the correct direction. They're in the anti-clockwise direction. So when you add up all of these, you're going to get the cancellation in the interior, and you're going to just be left with the integral on the outside. So it works. So Green's theorem just works. So what you get here is the integral of u dx plus v dy all the way around the outside. And what you get on this side when you do the addition is because you're adding that plus that plus that plus that, you're doing everything. So that's just going to give you the integral of this function over the entire integral. So it works. So even if R is not an elementary region, it still works, which is pretty nice. It turns out that you can push this even further. What if R is something even worse than that? What if it has disconnected regions, right? So R consists not of one region, but two, right? So it's the interior of that plus the interior of that. And then if you ask me, well, what's the boundary of R? Well, the boundary of R consists of two different entities. It's this curve over here plus this curve over here. So that's two disconnected entities as well. Right? So R is two disconnected things, and my boundary is two disconnected things. So notice that I put my arrows here in according to the convention that I had earlier, that I am going in the anti-clockwise direction. Okay, so that's the convention that we have. Okay, can I apply Green's theorem to this sort of complicated region? It's this plus this. Is Green's theorem still valid for this region? Yeah, where the region is that, and then the boundary is these two different curves. Well, here's what you do, right? Think of a two-way connection. Think of drawing a two-way connection, one connection in that direction, and I'm going in that way, and another connection in this direction. Okay, going in the opposite direction. And what I'm really going to be thinking of is I'm going to be thinking of shrinking these two things so they essentially collapse onto one another, right? But before I shrink them, if you look carefully at what I have here, so here I'm going in the correct direction, the anti-clockwise direction along this, but now I've got this added connection. So I jump over to this side and I'm going in the correct direction. Now I jump back over to this side and again I'm going in the correct direction. So what I've done here is I've created this new curve, but what's nice about this new curve is that it connects, it's one region that it encloses, and that region consists of this part, and also this really narrow channel that you have in between. Well, Green's theorem applies to this region. There's absolutely no reason why you can't apply Green's theorem to this region, and that tells you that the area integral over this whole interior stuff can be represented in terms of the line integral over this sort of this curve over here, right? So it's going to apply. Now, what I think of is I think of shrinking these two. So I make them go very, very, very close to each other. And if I do that, it's again the same argument as before, because for the line integral, I've got a line integral in that direction and a line integral in the opposite direction. And these two lines are going to collapse onto one another. So in the limit, I'm going to, whatever I'm going to get in this direction, I'm going to get negative that in the other direction because I'm traversing the same thing backwards. So when I'm doing the line integral, that and that cancel. So the line integral that I'm left with is that line integral, well, plus this line integral. Yeah, so that's great. So the line integrals just work out. What about the area integrals? Well, it's exactly the same thing for the area integrals. Because I'm shrinking this together, this region over here is going to vanish to nothing. It's going to have no measure from the mathematical perspective. So there's no size to that. So there's no contribution then to the area integral. So that means that your area integral is going to collapse to this plus that. So that's great. So that tells you that Green's theorem applies even to regions of this form. So regions in which you have your R consists of disconnected regions. You can have many disconnected regions, in fact. And where your curves, your boundary curves are these disconnected curves, it still applies. You can still write down the full conclusion of Green's theorem. Yeah. So an integral over R which is an integral over that and that, is associated with the line integral over dr, which consists of, in this case, two curves, right? So you can do this curve, we can call it C1 and C2 perhaps, and you can add those two things together. So that's pretty neat. But we can, yeah. So this is what I said, the green line integrals cancel since they're in opposite directions. Okay, so if R has disconnected regions, we're in business as well. Green's theorem still applies. Let's try to push this even further. What if R is not a simply connected region? So a simply connected region means something which has no holes. So what if R is not a simply connected region? What if it has a hole? So R in this case is like this this annulus. So it's not including the hole in the middle. So what if R is a region like this? Okay, now let's think about this a little bit. What is the boundary of R? Well, the boundary of R, I realize now, has to have two components, right? So there's the exterior boundary, that's the interior boundary as well. So there's two curves which comprise dr in this case. I haven't put down any arrows yet, and let's try to figure that out. Right? So can I deal with this using Green's theorem? Does Green's theorem still apply? And the answer is, well, yes. You do exactly the same little trick. What you do is you start on the outer boundary and you think you're going anti-clockwise because that was the right thing that we were asked to do. And at some point you draw a connection towards this. Right? And then when you come to this, you go in the clockwise direction. Okay, so notice you're going in the clockwise direction, and then you come back out and continue along this. Okay, so when you do that, you realize that you get this shaded region. So in the shaded region, so now this is nicely, it's a simply connected region. Every point is connected to everything else. So I can apply Green's theorem in the normal way. So when I apply Green's theorem in the normal way, what I'm going to do for my area integral is I'm going to get an integral over this. Okay, and that's going to equal a line integral, the corresponding line integral over this sort of complicated quantity that I have. Right, so that's my boundary in this case. My line integral is that. Okay, so that's fine, and so Green's theorem applies to this. Right, and again the same idea applies. The line integral on the connections will cancel because I'm going to think of shrinking these two connections to each other. So then I'm going to have one going in that direction, one going in that direction. They will cancel. So then I'm left with a line integral around that. But notice here that the line integral around this is in the opposite direction. Yeah, it's in the clockwise direction. This was anti-clockwise, this was clockwise. Okay, so that's one little thing which occurs. What about the area integral, the double integral? Well, that's fine as well, right? Because as these two things shrink to one another, this little deficiency cancels. So actually this coloring will color everything, right? So R is going to be the whole thing. Yeah, so it actually does work, but I have to be just a little bit careful here. So I have to update my convention. So now when I'm thinking of my boundary, it's not just anti-clockwise. So it would be anti-clockwise if it was simply connected. But if it has holes, in the holes, I have to go in the opposite direction. So it turns out that there's a very simple way of updating this convention. And that's to think of when you're traversing the boundary, always make sure that the relevant region is on the left, is towards your left. So as you're going along this, the region is towards your left. As you're going along this, the region is towards your left. And in this case as well, right, as you're going along this in that direction, the region is towards your left. So that's how you have to choose the directionality of your boundary curves in general. So here's a slight extension, and then this is always consistent. The region is always towards your left. So now what we established here is that Green's theorem works for all sorts of different types of regions, which is pretty good. Okay, so here's Green's theorem. Once again, I've just written down the conclusion of Green's theorem. It's that, and the point I'm trying to make here is that this is an interior integral. It's an integral over region, and this is an integral over the boundary. Yeah, for all types of R, this actually works. And again, to highlight that what I have on the left here is just an integral of this form. So it's a double integral over a function f of xy. Well, what is my function f of xy? Well, it's this particular combination of the two given functions, the functions u and v. I construct this combination of it, and then I do the integral I do a dA. And I just do this double integral on this side. What about the right hand side? With the right hand side, this is just an integral of the form f dot dr. As long as I make the identification where my vector field f has two components, u and v. So it's ui plus vj. Then when I take f dot dr, I of course get that. Okay, so this is the normal way in which you'll often see Green's theorem expressed, but you should really bear in mind that what's going on here is this sort of thing. It's an area integral, double integral, which is being related to an integral, line integral going around the boundary of the of that region. So in the next lecture, I'll do several examples related to this.